This is ELEC 1510 Logic Design Lecture 8 Video 1 on NAND implementations of circuits corresponding to textbook section 3.6. NAND gates are the complement of an AND gate, which means that we take the AND function of input variables and then take the complement of that. So that could be equal to an AND gate and then an inverter, or more simply a NAND gate, which looks like this. It's an AND gate with a bubble at the output. So for example, xy prime as a function would be drawn using a NAND gate like this. It's an AND gate with x and y as inputs and a bubble at the output for a complement. So that's a 2-input NAND gate. A 4-input NAND gate, or even more inputs, can also be drawn. So that's totally legitimate as well. W, X, Y, and Z as inputs into a 4-input AND gate, and then a bubble at the output representing the complement. So that would be the NAND function. So why do we want to use NAND circuits? Well, basically all real logic circuits on integrated chips are actually designed using NAND gates in general, because NAND gates are the most electronically efficient way of designing circuits. An OR gate, like this, is a nice little logic symbol, but it's actually pretty difficult to build electronically. The simplest one to build is a NAND gate. This one is actually very, very easy to build electronically. So while it's not quite as conducive to designing simple logic equations, this one is very efficient, which means less money involved in designs. Money goes down. So that's why we want to design things using NAND gates. All right, so let's dive more deeply into complementing terms. We already know that if we add a bubble to the output of an AND gate, it's called a NAND gate because it negates the output. For example, we can also add a bubble to the output of an OR gate. That is called a NOR. If the two inputs are x and y, this is the function x plus y complement, or what we would call NOR. We can add bubbles to the inputs of gates as well. So let's take an OR gate and add bubbles to both of those inputs. This doesn't have a name, convenient name like NOR, but it does perform the function x prime plus y prime. So that would be just another way of complementing those input variables. We can also complement both inputs and outputs. So now let's draw an AND gate with complements on its inputs, x and y, and on the output. So now this is simulating the function x prime y prime prime. Okay, so sometimes we need to actually just take the complement of a single variable to create the literal of its complement. Now conveniently, x and x parentheses prime is just equal to x prime. So that means that we can take x and input it into both inputs of a NAND gate, and on the other side we get x prime. So that's how you create the complemented literal in the case that you need that for your circuit using a NAND gate. So now it's important to be aware that double complementing cancels out. So for example, if I draw the function x, y into an AND gate, so now f is equal to x, y. If I add bubbles to those inputs and complement the variables, now I have x double prime, y double prime, which is back to xy. So double complementing cancels out. This can either be done with primes or with bubbles. So let's say I have a more complicated function now, where f is going to be equal to a product of sums with w, x, y, and z. And if I add bubbles to the outputs of the OR gates and bubbles to the input of the AND gate, those will cancel out. Any two bubbles on a single line cancel each other out. And so I'm back to the original function. That's going to prove very useful for us in the future in manipulating how these circuits look. Okay, another basic bit of theory that will help us create NAND circuits is DeMorgans theorem. So let's say that I have a function x or y or z. We would draw that using an OR gate as x, y, z, all inputs to an OR gate. If I double complement all of those inputs and redraw that function, I get the same thing because double complementing cancels out. I'll draw one of those complements as bubbles, and I'll add primes to represent the other complement. So again, every double complement cancels out. So it's perfectly legitimate to, on the picture, complement all of the inputs and then add bubbles to all of the inputs, and those will cancel out. Now, when I take DeMorgans theorem for this function, I get rid of one of the complements for each input variable, and then I change the operation to AND instead of OR, and then I complement the output. That's what DeMorgans theorem does. And so now, drawn as a circuit, this would look like x prime, y prime, z prime as inputs to a NAND gate. And so what you can see here is that for the inputs x prime, y prime, z prime, input to an OR gate with complemented inputs, that is completely equivalent to a NAND gate. So OR gates with complemented inputs are the exact same thing as a NAND gate. And that will help us to transform logic circuits visually from sum of products type circuits into NAND gate circuits. So let's do an example of this first, looking at it algebraically. We have function of x, y, and z is x, y prime, or z, or x prime, y. Now this could probably be simplified somewhat. I see a way that we could implement it using an XOR circuit, but we don't want to do that. NAND gates are much more electronically efficient, so we're going to create it using NAND gates. So what I'm going to do first is actually double complement the whole expression, which will cancel out x, y prime, or z, or x prime, y, all double complemented. And I'm going to use one of those complements in DeMorgans theorem, which gets me to xy prime, parentheses prime, and z prime, and x prime y, parentheses prime, all prime. Now what you can see is that everything in this entire circuit is implemented as a product of variables prime. So that's all NAND gates. So let's draw that. First we have x, y prime, parentheses prime, so that is input to a NAND gate. Then we have z prime. Again, I'm just using the complemented variables as literals. I could have created those literals, the complement of the original variables, using that variable input as both inputs to a NAND gate, but I'm going to actually just draw them using literals for right now. So that's another input. And then finally, x prime y as the inputs to another NAND gate. And then all of that is taken together using a 3-input NAND gate. So now, as you can see, I have implemented that entire sum of products expression just using NAND gates, which is the most electronically efficient way to implement it. Now let's do that same operation visually. So let's draw the original circuit, the sum of products version, which will have x, y prime input to an AND gate, then simply z, then x prime y input to an AND gate, and then all of that input to an OR gate. Okay, so as I showed several slides ago, if you complement the inputs of an OR gate, that is equal to creating a NAND gate. So I want to complement these inputs by adding bubbles to them visually, but I can't do that because I'm changing the logic. So what I need to do is cancel out those complements by adding bubbles to the other end of each of those wires. As long as I have two bubbles on a wire, those complements will cancel out and I'm good to go. So on the other end of each of those wires, I add another bubble. And now I visually change those gates or the bubbles into NAND gates. So as you can see, this already became a NAND gate by adding the bubble. This became a NAND gate by adding the bubble. This will be transformed into a NAND gate. And then I can just complement z. And so what I'll have is x, y prime input to a NAND gate, z prime and x prime y input to another NAND gate, and then the 3 input OR gate with the complemented inputs just becomes another NAND gate. And this is the same circuit that I derived using DeMorgans' theorem on the previous slide. So it's totally legitimate to create the NAND circuit out of the sum of products expression either algebraically by using DeMorgans' theorem or adding 2 bubbles to every line that has an OR gate in order to create all of the NAND gates.